Okay.
I'm trying to get it as close as possible to an old-fashioned blackboard for.
That's nice. Okay. So let's start. So the last lecture today is by Henry Maxfield, and he's going to tell us about black hole information and space-time wormholes. Take it away, Henry.
Thank you, Shota. It's wonderful to be giving these lectures today to try to explain some of the exciting developments that have been happening in quantum gravity in the last couple of years, and at the end we'll end in a difficult situation with lots of open questions. So I hope that some of the people listening can contribute to helping us unravel some of those in the future as well. So the outline of the talk is I'm going to start off trying to go relatively quickly through things that may be familiar to some, talking about sort of familiar old material about quantum black holes. And one of the main things is in today's lecture, we'll try to construct a very simple model of an evaporating quantum black hole that that captures lots of the sort of interesting physics that we want to study, but is kind of quite easy to study. So it'll be laying the groundwork today to get to some of the more interesting stuff in later lectures. Once we've got that under our belt, then we're going to start talking about entropy. So we're going to start off by talking about entropy and just very generic quantum systems and what we expect, what we should expect from quantum mechanics, before then asking what happens in gravitational situation. And in particular, this is probably in tomorrow's lecture. Hopefully we'll get as far as talking about these replica wormholes, and these have played an interesting role in understanding the entropy of these black holes. But these also raise some puzzles, and that's what we're going to start talking about in the sort of second half, because these are an example of what's called space-time wormholes. We'll explain what that means when we get there. And these were studied a long time ago and lead to some puzzles about long-distance correlations and sort of non-local physics, and we'll explain those ideas in some generality and give some other recent applications. And then finally, we'll be able to use that and try to understand what these replica wormholes are telling us. But the philosophy throughout these lectures is going to be concentrating on having some low energy theory of gravity. So we have some effective field theory, so maybe it's Einstein Gravity. So you might think of, in 4 dimensions, we're interested in studying an action like Einstein Gravity, plus some, plus some matter action. Maybe this is the standard model, and treating this as an effective field theory. And so it's a very conservative point of view, but we really want to make sure we understand what the low energy theory tells us. So in particular, I'm going to try to avoid as much as possible using ingredients from some kind of short distance UV completion of the theory. So I'm not going to use anything like strings. In particular, I'm going to try to avoid using any sort of holography or ADS-CFT as much as possible. And these kind of things. I'm not going to assume any of these sort of more exotic things. What I want to start from is an effective field theory about physics that we know well and have tested in our own universe. Make sure we understand this first, and then we'll try to put it in these contexts of these other ideas later. Okay. And in particular, the interpretation we get to at the end here, from taking this low energy point of view very seriously, is not going to be completely lined up with what we expect from things like ADS-CFT, and that'll be the sort of subject of the very end. Okay, so let's get started. I'll try to pause sort of fairly regularly for questions. I should be able to see if anything comes up in the chat window. So, do if there are other if you don't want to ask your questions live, then feel free to put them in the chat as well. Okay, so let's start off talking about black holes. And in particular, we're going to talk about the geometry of event horizons. And this is probably going to be familiar to most of you, so we'll try to go through this quite quickly. So first of all, when a black hole is collapses, say in just in classical general relativity, we expect it to, once it stops collecting matter, to very quickly settle down to something static. And just for simplicity, I'm going to take black holes that don't have angular momentum. So we'll look at some spherically symmetric spacetimes, and we can write a general static spherically symmetric spacetime in these sort of ingoing coordinates. So these will be one of the coordinates we use. And there's some sphere here that I'm going to, so you may be a term something like r squared d omega squared, where this is a sphere. I'm just going to ignore that because the sphere is not going to play a particularly important role in what we're doing at the moment. So the picture here is something like this. We're going to be slightly general about what the metric looks like asymptotically. So this is a Penrose diagram of asymptotically flat metric, and I want you to imagine that this metric isn't we don't have this metric for all time, but instead it's just going to apply after some initial time. So maybe we've got some star that's over here that's collapsing, and there's some matter going on, but once we're after some moment in time here, so maybe there's some time v0, and after that ingoing time, the essentially all of these details about what formed the black hole are not important for the geometry anymore. And we'll see kind of explicitly in our simple model how that's realized. So the geometry to the future of this v0 is going to look something like this, at least classically. So this function f is going to go approach 1 at large values of this radial coordinate r in the asymptotically flat case, and it's going to go like r squared over l squared in the ADS case. And just to emphasize what this v coordinate does, it's constant on ingoing light rays. So it's constant along these sort of lines. Okay, and we also define v so that if we had some distant observer, then their clock would match the value of v. So, okay. So that's just sort of setting up the coordinates for this general metric. So let's now look at outgoing null geodetics. And just reading it off from the metric, we can see what paths these outgoing geodetics follow. And in particular, if this radial coordinate that defines the distance away from the black hole is decreasing, then it means that this outgoing light ray is not going to make it to infinity. So in particular, if this function f has a 0, then we're going to get an event horizon. Okay, so we'll define this RH as the largest 0 of this function f. So just solving this these outgoing null geodetics, then we can in general write them in terms of an ingoing time. So this gives us a useful coordinate in terms of this ingoing time u, and u is going to be now constant along lines like this. So u is increasing in this direction. So here's so in the ADS case, if you're outside the black hole, for example, you can determine your coordinate v by shining a light ray back and hitting the boundary at time v, and shining it forward, and it hits the boundary at time u. And in particular, the boundary here of ADS will be at u equals v. And some point in the middle will be at some value of u bigger than v. But of course, this only covers the outside of the event horizon. So we'll be interested in what's going on at the event horizon itself, so we'll need a different coordinate. But this will be another convenient coordinate. Okay, so let's look at what's going on near the horizon. And generically, this f has a 0, so it's going to vanish linearly. And the coefficient here, the derivative, is going to be given by this kappa, the surface gravity. So we can now solve this, this geodetic equation using this approximation in the near horizon, and we'll get something like this with some integration constant a. And the thing to notice in particular is this exponential dependence on V. So that means that if we start near the horizon and we follow it outwards, so these outgoing null geodesics live at fixed values of U, and V is a parameter along the geodesics. And as we move forward in time, we get this exponential growth. So the geodesic is exponentially diverging from the horizon. So this seems like a sort of innocuous fact, but this is the crucial piece of the geometry that underlies a lot of the interesting physics of horizons and Hawking radiation in particular is what we're going to see. Okay, so using this fact, we can now look at this near horizon metric in these light cone coordinates, and it looks something like this. Okay, so this is our near horizon metric. This is just plugging in our new light cone coordinate. And I'll just re-emphasize this fact until we get used to it, that U and V are coordinates that are constant along light cones, but the way you sort of calibrate them is by measuring them at infinity, very far away. So emphasize this fact that that they're measured, for example, in the ADS case by the boundary time matching these light cone coordinates. Okay, but of course we know that if we look locally at any geometry in a small enough region that's much smaller than the curvature scale of the geometry, it's going to look approximately flat. And actually, we can see that this is a flat metric. So in particular, we can define these new coordinates, capital U, capital V, sort of Kruskal-like coordinates, with its exponential dependence on small u and small v. And once we've done this, coordinate change to these Kruskal type coordinates, we get the familiar flat metric in light cone form. So u is roughly t minus r, and v is roughly t plus r. And the thing to emphasize now is that this u, while this small u was not a regular coordinate of the horizon, it goes to infinity as we approach the event horizon. This capital U is a regular coordinate. So this is this describes the geometry in a smooth way in the vicinity of the event horizon, both inside and outside. Okay, so that's mostly sort of setting up notation and the sort of coordinate systems we're going to be using. So let's now consider what time translation looks like in this metric. So time translation acts on these light cone coordinates just by shifting them by some delta t. It should be delta t, I suppose. But so that means because we've defined these capital U and capital V coordinates with the exponentials, these time translations in these near horizon flat light cone coordinates become these exponentials. So another way to say that is that there's a killing vector that defines time translation, and in the near horizon it looks something like this. And this is a familiar sort of killing vector. This thing is a boost. And so one way to think about this is that the Hamiltonian that's generating time evolution in the black hole background, in the near horizon, it looks like this surface gravity kappa multiplied by a boost. Okay. So because of the state now at the event horizon, there's nothing. Of course, the event horizon is a perfectly smooth place. So we're looking at some vicinity of the event horizon in these coordinates u and v, and we'd like our column fields to be perfectly regular there. There's nothing obviously terrible happening. So if we look close enough to the horizon, then any state looks approximately like a vacuum. So we look on some length scale that's much smaller than the typical sort of excitations that are the typical energy density. and our state is going to look locally like the vacuum. So let's now ask what that looks like in terms of this K. This is a sort of heuristic argument that we'll use more carefully and look at more carefully in an example. But the crucial fact that is that in any relativistically invariant quantum field theory, if you look at the vacuum state in terms of this boost generator, then it looks thermal. So the basic idea behind this is to imagine you define the vacuum in some lower half plane by a path integral. So this defines the vacuum by doing some Euclidean path integral. So that means doing a Euclidean path integral computes time evolution for you. So you're computing e to the minus h times some Euclidean time, and you take Euclidean time to infinity, and that projects you down to the vacuum. And up here, this is producing something similar. In the upper half plane, you get this is producing the sort of kept version of the bra version of the vacuum state. And if we want to just talk about the state on a half space, then we can just trace over the fields on one half of the geometry. So this is, for us, is going to be the inside of the horizon, so the black hole interior. And that means that we sort of glue together our path integral. We're going to talk, if these path integrals aren't familiar, we'll talk about them in more detail later when we talk about entropies. So don't worry if this is not making a lot of sense for now, and this is just a heuristic anyway. But now in Euclidean space, K, this K generator becomes a rotation. So a boost in Lorentzian space becomes a rotation in Euclidean space. So to compute this path integral, instead of doing it by time evolution, by the time that runs forward and backwards vertically, we can do it instead by a rotation. So in particular, the density matrix is computed by evolving from the bottom half of this cut on one side to the top half of this cut from the other side. So it's a rotation by 2 pi, and that's precisely what this density matrix is. It's a 2 pi rotation in Euclidean space, and that's what's computing this state on a half space. But of course, this is the form of a Boltzmann distribution. So this looks thermal. And this is the famous Rindler temperature. So it means that the vacuum near the horizon, if you express it in terms of the Hamiltonian asymptotically, looks like a thermal state. And in particular, the temperature of that thermal state is given by the surface gravity. So the near horizon, if you're a distant observer, there's a sense in which the near horizon looks thermal. And this is, so far, is just sort of suggestive, but by more careful calculation, it's borne out that if you're really sitting at infinity, then you'll see a flux of thermal radiation that's coming from that's produced in the vicinity of the horizon. So, so this is the temperature of Hawking radiation. Okay, so we're not going to go through the derivation, the careful derivation of Hawking radiation in great detail, but instead we're just going to talk about it in a extremely simple model where we can solve everything. And in fact, in terms of the energy momentum, the dynamics is determined completely by symmetry. So that'll be the next thing. We'll talk about this conformal matter in 2 dimensions. But I'll just pause briefly in case there are any questions about the setup. So in particular, we're going to be using these various coordinates, these ingoing coordinates and these light cone coordinates and these critical coordinates, sort of versions of these throughout. So if it's not obvious what these things are, then ask now. Okay, good. So hopefully it's familiar to everyone so far. So we're going to use a very simple model of a conformal field theory in 2 dimensions. So we're going to take two-dimensional spacetimes, and this could be something that's sort of strongly interacting. It could be very complicated, but that if you want something concrete, you can think of this as being, say, a free massless boson or a free massless fermion. And in fact, this would be if there happened to be a massless scalar in our universe, then this would be an excellent approximation for the radially symmetric radiation from say a short-shell black hole or something. So the important thing of a CFT, we're not going to hopefully be requiring too many details of what sort of background in 2D CFT. I'll introduce the things we need along the way. The important thing is that rescaling the metric is a symmetry. So if we take our metric and we can solve the theory living on some metric G, then if we multiply G by some Weyl factor, omega, this could be it's not just a constant necessarily, but depends on space-time, then we can also solve the theory on this different space-time metric. And this is telling us something about the trace of the stress tensor. So the stress tensor is in a classical theory. I'll just note the convention here because often in the 2D CFT literature, this is not a -2, it's a 4 pi. So there's a factor of -2 pi that's different from CFT. But this is the usual convention in relativity, for example. And so this is the convention where T00 is the energy density. Okay, so the stress tensor is telling us in the classical theory about the variation of the action of the theory with respect to the metric. And in particular, if you change this Weyl factor omega, that means that this change of the metric is diagonal. It's proportional to GAB itself. So that means that that we end up asking about the trace of the stress tensor. So in the full quantum theory, this is going to be telling us about the derivatives of correlation functions. But instead, okay. If this was a symmetry that didn't change anything, then the trace of the stress tensor would vanish, and that's exactly what happens in flat spacetime. But this actually has an anomaly. It's a famous Weyl anomaly. I won't go through the details and derivation and so forth. I'm just going to use it as a fact. This is discussed nicely in, for example, in Polchinski's volume 1 of Polchinski's string theory book. But it tells us that the trace of this stress tensor it's not 0, but it's something that's determined completely by the geometry. So it's this geometry we're regarding as some fixed thing, and it's given by the curvature up to this factor C, and C is the central charge, which tells us sort of how many degrees of freedom there are. Okay. So this trace T is not some non-trivial operator. It's really proportional to the identity operator. Okay. And so we can write this in terms of some Lycone coordinates, like our UV Lycone coordinates we had before, and we get some formula for the trace of the stress tensor. But this is really useful in 2 dimensions because there are 3 independent components for the stress tensor, and there's already 2 equations for it that we always have, namely the conservation equation. So we always have these conservation equations, which there are 2, the U component and the V component. And once we've got this 3rd equation, it means we have 3 equations for 3 unknowns, and we can basically solve everything. So CFT is wonderful because the 2D CFT has the wonderful fact that the dynamics of energy and momentum is determined fixed completely by symmetry. This, of course, is not true in higher dimensions or in generic theories. You have to know what energy is produced and how it evolves. You have to know something about interactions and so forth, but not so in 2D. So this is the sort of underlying origin behind Virasoro symmetry and so forth, but we won't be using any of that. Okay, so this is this is what you get by solving the conservation equations. So roughly speaking, the conservation equations tell you something about the, say, the v derivative of TUU, and in particular, there's some inhomogeneous term that comes from the trace. So the v derivative of TUU would be 0 in flat spacetime. So you'd have an equation like this in flat spacetime, but in curved spacetime, there's an extra component that comes from the trace of the stress tensor that you can comes from this. So you get something inhomogeneous. Okay, and in particular, we can interpret these terms. So there are some unknown functions of u, and this factor here out the front is exactly 0 in flat spacetime and in ADS spacetime. So these terms are going to vanish. They're going to be 0 very, very far from our black hole in our asymptotic region. So that means that FUU is the value of TUU asymptotically. So this is an asymptotic outgoing energy flux. So this tells us how much energy is escaping from our black hole. And this function is the same, except it's an ingoing energy. Okay, and I should say I'm just finishing off writing up my notes for this, and I'll perhaps, if people would like access to the notes as I go along, then maybe I can put a link to sections of the notes in the Slack channel or something. But there are a few exercises in it. The first one here is to check when these terms actually reduce to, so if this is a function of u and this is a function of v, then these reduce to the usual conservation equations. Okay. And it's checking what spacetimes that's true for. Okay. Fine. So we have these conservation equations that if we know the energy that's incoming from infinity, and we know the energy that's going out to infinity, then we know the stress tensor everywhere in the spacetime. We just trace back the ingoing energy and trace back the outgoing energy, and that tells us what the stress tensor looks like at any particular point in terms of this Weyl anomaly. Okay, so I should just say that I've written this in terms of a sort of classical stress tensor. In the quantum theory, this is going to be still true as an operator equation as long as there aren't insertions of other operators. So this will get some sources if you have if there are other operators sitting in the path integral, but for us, they're just going to be, these will be valid for the expectation value of the stress tensor in any state. Okay, so let's take these now and go to our near horizon geometry. So we wrote down some light cone coordinates for our near horizon earlier, and they had this exponential form. So this little omega, remember our metric is minus e to the 2 omega du dv. So this exponential form of the metric, again, this is the geometry of this is the fact that geodesics in the near horizon are diverging exponentially. It's given by this linear thing. So you just plug it into the formulas above, and we find these two formulas. So, well, we find, first of all, this formula for TU. Okay. So, so we've got this shift. So the sort of outgoing flux of energy in this u coordinate in the near horizon regime is shifted relative to the flux asymptotically. But let's now, this little u coordinate, remember, was not a good coordinate at the event horizon. So if we want to know physically what's going to happen if someone falls into the black hole, for example, then we need to go to some coordinate that's regular at the event horizon. So this ingoing coordinate is a good option. And this, you get a factor of, this is just a factor of du by dr squared. in the denominator. And what we should notice is that if the flux of energy and momentum at infinity vanishes, then this energy density, so TRR is like a pressure density or something. But actually, we're not in. We're in some ingoing Lycone coordinates. But okay, there's some energy density, some component of the energy momentum tensor at the horizon is going to blow up. It has this kind of singularity. So if there wasn't energy flux in infinity, then the state would be singular at the horizon. On the other hand, if we want this to be non-singular at the horizon, then we need this FU to have some term that cancels this. And in terms of the Hawking temperature that we wrote down earlier, there's a formula that looks like this. And then the correction terms have to be no bigger than this denominator. And in terms of the U coordinate, so remember this R minus RH is related exponentially to the small U coordinate. The correction terms are decay exponentially with this coefficient of kappa. And now, this is something interesting. This FU has, we interpreted it up here as the energy flux that someone very far from the black hole measures. So it means that if we have any state at all that is regular at the horizon, that doesn't have an energy density that's blowing up, then we get this constant flux of energy out of infinity. And this is the energy density or the outgoing energy density of a thermal state. So this is at temperature TH. So we had this very heuristic argument earlier that the Hamiltonian at infinity looks like a booster in the near horizon. So the state in the near horizon looks thermal in some sense. And here that's being realized extremely concretely. And we can, and we're seeing this is working in a very, very generic situation. We didn't have to assume much at all about the geometry. We only had to assume, look at this near horizon geometry and assume the state was regular at the horizon. And we've got this conclusion. Of course, in higher dimensions, there's this is a little bit more involved, and in particular, the radiation can scatter off the background. So not all you can sort of produce thermal radiation near the horizon, but not all of it escapes. Some of it gets pulled back into the black hole, and life is a little more complicated. But the basic result is the same, is that you get this sort of flux of thermal radiation. And I'll just mention the interpretation of this term. So this is, you can sort of think of it as a very simple version of a quasi-normal mode. So a quasi-normal mode is a thing that describes the approach to equilibrium of a black hole. So you start with a static black hole, and then you just perturb it slightly in some way. Then you ask about the linearized perturbations, and these things decay away as radiation goes out to infinity, and they decay away with some rate, and which is typically of the scale of the size of the black hole. And this is a very simple version in this two-dimensional examples of a quasi-normal quasi-normal mode. Fine. Yeah, so this is in particular telling you that if there may be some extremely complicated state and with a star that's falling into the black hole and lots of energy that's crossing the horizon in the distant past, but whatever that it looks like, you have to wait a few times 1 over kappa. So it's there's a time which goes like 1 over kappa. And if you wait a few times 1 over kappa, then all of these details as to what fell into the black hole originally are getting washed out. It's decaying exponentially. So very, very rapidly, we approach this, this static situation. So this is a sort of self-consistency check of this result earlier, that the black hole should approach something static, and okay, on this sort of timescale.
Sorry,
So
it's a little hard. Sorry, it's a little hard to see what sits in the exponential. It's e to minus 2 kappa u.
It's e to the minus 2 kappa u. Yeah, sorry.
Okay, all right, thanks.
Maybe this is the other thing I should have mentioned earlier, is if I've got a trade-off between how much I can have to see at one time and how big I'm writing. So
Well, it's okay, yeah. I guess like people can also ask questions if they can't read, so.
So it's okay. Exponents are getting a bit too small, but otherwise it's reasonable.
Yeah, I guess so. Yeah, at least for me.
If other people disagree, I want to accommodate to the person who's struggling the most. So okay, well, if there's something that you can't read, then let me know, and I'll make it legible. I'm being told that the size is okay, but the quality isn't great.
Henry, is there any chance that you will post this scanned notes to the Slack so that people who?
Yeah, I'll probably what I'll do is depending on how quickly I can polish it off, I can try to I'll have some sort of LaTeX notes with a few more details and so forth. So.
Thanks.
But I can scan this as well.
Yeah, actually, there are several complaints in the chat. But I guess
one thing I can do to increase the quality is make it so we see less. And well, I think I'll struggle to make a big difference today, but I'll try to bear it in mind for tomorrow. Yeah, so if there's something that isn't legible, then let me know today, and I'll.
Yeah, I think it's a little better now. Thanks.
Yeah, sometimes the camera doesn't focus properly as well. Okay, so we looked first at this TUU, this outgoing energy, and because of this mismatch between this term gives us a mismatch between infinity and the horizon. We're getting this this flux of energy out of infinity, and okay. So now let's look at this TVV component, and we get essentially the same formula. And now the flux that's coming in from infinity, now the flux coming in from infinity is something that we can decide. It's that's something that maybe we as experimenters have control over. We can decide what we're going to throw into the black hole. So in particular, if our black hole is sitting in isolation without anything coming in from infinity, then TVV is given by this, the horizon is given by this minus kappa squared formula. So there's a negative energy flux across the horizon. And when we apply this to when we allow the metric to become dynamical and evolve, this negative energy flux is going to back react on the metric and is going to make the black hole shrink, evaporate. So this is the sort of counterpoint. You've got this flux of energy coming out at infinity, and if you want to conserve energy, then you better lose it somewhere. And the place you're losing it is this flux in through the horizon, which is subsequently going to back react on the black hole. So this is the source of evaporation. Okay.
So there is one question in the chat.
Yes. So yeah, so the answer hopefully is that if you just look at this, so we have this singularity in the denominator. So maybe I should, up to some constants, r minus r h is this is proportional to e to the minus kappa times u. So this is the fact that geodesics diverge exponentially. That's right. with a minus sign. No, that's right. So the distance from the horizon is this exponential. So it means that that if we want this to remain finite, then the denominator had better go to 0. So the denominator is going to 0, so the numerator had better go to 0 as well. And the numerator better go to 0 at the same rate. So we need that fu of u is going to be c over 48 pi times kappa squared plus some number that's proportional to r minus rh squared. And then there could be higher order corrections. Maybe another way to think about this is instead of starting with this and asking what the energy density of the horizon is, let's start asking what is the energy density of the horizon, and then read off the energy density in infinity. And so if you move this denominator over to the left-hand side, if you have any finite energy density of the horizon, then once you multiply it by this, it goes to 0. So yeah, I've just used different variables. Hopefully that clarifies it a bit. I wasn't sure whether. Yeah, maybe that's a better way to think about it, is you start with the flux. This is more like an initial condition on the left-hand side, you know what the energy density looks like at the horizon, and then you can solve for this fu of u, the flux infinity. Okay, so let's. I'm just going to talk now about ADS. So the model we're going to be using earlier is going to have anti-de Sitter asymptotics, and if you want to have some sort of energy conserving evolution in ADS, then you have boundary conditions that reflect. So this boundary is at u equals v equals t, where t is the sort of physical time asymptotically, and these would be the boundary conditions that are required if you're doing ADS-CFT, for example. But any sort of energy conserving boundary conditions are going to satisfy the fact that the outgoing flux at the boundary is equal to the ingoing flux. So the picture here is just that you have some outgoing energy, then it's got to bounce back in. So this is fu of u, and this is fu of t. And any energy that's coming out to the boundary at time t is going to reflect back in. So these two things have to be equal. And but we like to have our black hole model what happens in asymptotically flat space, for example, or we'd like our black hole to be able to evaporate. So to do that, we're going to couple the system to another system. So this is just because of conservation of energy. But if we couple the black hole to another system, then the energy can flow between the two. So this over here so this is our reservoir. And this is going to be a fixed flat spacetime. So it's going to have metric minus du dv. And it's in the region where this ingoing time is bigger than the outgoing time. And we're going to have the CFT live on this half space. So this is half of Minkowski space. With our matter CFT living on it, but we're not going to have any gravitational dynamics. It's just going to be this fixed, rigid, flat metric. And if you like, you can think of this as a model for what happens in asymptotically flat space, very, very far from the black hole. We don't expect back reaction gravitational dynamics to be important. So it's a good approximation to consider a crude approximation. You replace it with some fixed spacetime. And here on the left-hand side, this is going to be our gravity is going to live here. And this is going to have dynamical gravity with our CFT. So in particular, our metric is going to be ds squared is minus e to the 2 omega of uv du dv. And this, and in particular, this is dynamical. This is in the region u bigger than v. So omega is going to be determined by the dynamics, in particular the dynamics of the energy. Okay, so this is, and then we're going to have, so these little u and little v coordinates only cover this region, so the exterior of the event horizon. But of course, we can pass to some other coordinates that, for example, these sort of ingoing coordinates that cover the interior as well. And then, because this geometry is a Weyl transformation of flat space, we can just first of all solve our matter CFT on this flat space. Ds squared is minus du dv. So this is using our basic fact about CFT is that if you solve it on some metric, you can do a Weyl transformation, and it tells you how to solve it on some other metric. So in this case, the Weyl transformation is going to do nothing over in this reservoir region, and it's going to do something in this ADS region. Now, this something is going to be singular as it approaches the horizon, but that's as it approaches this boundary. Sorry, omega is going to go to infinity, but that's not a problem. We can define the theory with this. So these are sort of completely transparent boundary conditions. In this frame, in the UV metric, it's like the boundary just isn't there. And the only thing that the boundary does is separate the region where we have gravitational dynamics from the region where we don't. Okay. Fine. Are there any questions about this? So this is a sort of a transparent boundary. At u is equal to v is equal to t. So this t is the physical time. Okay, so the last thing we can do now with our, before introducing, so far we've just been talking about quantum fields in a fixed black hole background, but we now have enough to introduce thermodynamics. So in particular, we saw on the, in particular, we know that that if we tune our flux from infinity to be to match, so the left-hand side and the right-hand side match, which means we have incoming thermal radiation at the Hawking temperature, then we're going to get zero stress tensor, and our black hole is going to stay static. So it's going to be in equilibrium. So we can place this black hole in equilibrium with some radiation at a particular temperature. And you could do that extremely explicitly in this sort of model. So that means the black hole has this temperature. That's sort of what temperature means. That's the zeroth law of thermodynamics. But we also have an energy of the black hole. Just by conservation of energy, or by there's some asymptotic form in the metric, like an ADM energy, something like that. You can define an energy for a static black hole in equilibrium. And if you know the dependence, the relationship between energy and temperature, then that's enough to use the first law of thermodynamics to determine an entropy. The entropy is given by integrating this relation. So the energy and the temperature are things that are determined completely by the geometry. So the energy by the geometry asymptotically, and the temperature by the surface gravity. Now, in Einstein gravity, and very generally, this entropy that you get this way has an extremely simple formula, a very famous formula. It's given by the area of the horizon in Planck units. This seems extremely magical, the fact that the entropy should depend on something that's a local feature of the geometry at the horizon. We'll see why this is true later on when we talk about gravitational entropy, why this is true in complete generality. is this is not just true of Einstein gravity. Any diffeomorphism invariant theory of gravity will have a formula something like this, where this entropy defined in this way is given by some geometric property of the event horizon. So the burning question now is to ask whether this thermodynamics has an ordinary quantum statistical description. So whether this Bekenstein-Hawking entropy is something like
Henry, I'm sorry to interrupt you with a technical glitch remark, but it might happen. We learned from the IT support that the live webcast might become off at 7 p.m. So we're not sure if it will happen, but if it will happen, we apologize and hope to fix it next days. But please continue. Just if people.
When did I start? I just want to.
You started, I think, 10 minutes past.
Yeah, you still have like a 10 to 15 minutes.
Yeah, you still have 10 to 15 minutes.
So hopefully we'll get through what I want to say. Okay. So we'd like to know if this Bekenstein-Hawking, this black hole entropy, Bekenstein-Hawking entropy counts. Okay, so it's time now to talk about gravitational dynamics. So we've got as far as we can get by talking about quantum fields on this fixed black hole background. We want to let our black hole be dynamical, and to do that we need some gravitational model. And in 2 dimensions, your first guess is to try Einstein gravity, but this has a problem in 2 dimensions, that it's topological. So one way of saying this is that if you compute the Einstein tensor in 2 dimensions, this is exactly 0 in 2D. So the variation of the action locally is 0, and you can't couple this consistently to matter, and you don't get a sort of interesting theory in 2D. You can do the next simple thing. So you introduce a scalar phi, which is we call it the dilaton, and you can write down this action. So in particular, the important thing here is this term where the curvature multiplies the dilaton. And this might look very arbitrary for now, but I'll just comment that this is something that is actually incredibly natural, and it's in particular, if you look at the near extremal limit of black holes in higher dimensions. So if you look, for example, at 4D charged Reisner-Nordstrom black holes, then you get this theory. So there's an Einstein-Hilbert term which describes the exactly extremal black hole, and this term, the J area of the horizon, which you can think of as the area at extremality plus some term proportional to the dilaton, and this is a small deviation from extremality. So this phi you should think of as describing the transverse area of some sphere in some other higher dimensions in this example. Okay, so you can see already why this theory is extremely simple. It's because this field phi just appears linearly. It's like a Lagrange multiplier. We can integrate it out, and it imposes the constraint that whatever it multiplies vanishes. So we get this constraint that r is -2. So we only have to consider constant curvature metrics. So this isn't just an equation of motion. This is like a delta function in the path integral. It's like a constraint on fields. Okay, so this is the theory. I've got to also tell you about the boundary conditions. So we're going to put so r is -2, so it's got anti-de Sitter asymptotics, ADS, and we're going to be putting our boundary near this asymptotic boundary of ADS. And in particular, the dilaton is going to be very large. It's going to be some number, some fixed constant gamma, that we're going to take. So we're going to take phi to infinity in this way, and the important thing here is that these surfaces of constant phi, the proper time along these surfaces, is going to define this sort of physical time. So t is the physical time, and it's related again. So it's because there's this infinite redshift as you go off to infinity in ADS, that you need this factor of epsilon. But this is a proper time that's measured from an observer far from the black hole. Our boundary is at u equals v equals t, and in particular, it's that physical time that we're going to use using t defined in this way. Okay, so now let's look at this theory in ingoing coordinates, and you can compute the curvature scalar in ingoing coordinates. It's just given by the second R derivative of this factor f, which we know is set to be -2. So it means that we are always, throughout not just classical solutions, but in the full quantum theory, your most general metric looks like this. So if there was a static metric, maybe familiar sort of ADS black hole, this wouldn't depend on V. This is, so it means that the only metric you have to consider are like this. This is sometimes called a videometric, where you take a static metric and let the size of the horizon depend on the ingoing time. But this turns out to be the full set of configurations that we have to consider in JT gravity. And now we can do notice something sort of wonderful here, makes things extremely simple, is that once we've imposed this constraint that R equals -2, the bulk term in the action disappears completely. It's 0. And we're only left with this boundary term. So this and this sort of, you can see this factor gamma comes in with for the boundary condition of the dilaton. But you can just compute what is the K here is the extrinsic curvature of the boundary, and you can compute that the extrinsic curvature of a surface of constant R in this metric. It's a simple exercise. And you find that it's that you get in the epsilon goes to 0 limit here, you get this extremely simple formula. And in particular, from this you can just read off be true for any metric we have to consider. But let's now specialize to begin with and ask about classical solutions where we don't have any matter. So we've already imposed the dilaton equation of motion. We can impose that as a constraint. But there's also an equation of motion for the metric. And you can think of this if you, okay, it's given by this. Again, it's a simple exercise to go and vary the metric and check that this is what you get. The analog of Einstein equations, if you like. And again, you can solve this. So two of the components tell you this, that there's a very simple solution again, that phi is completely independent of V, and it's essentially just given by this radial coordinate. So that's sort of familiar here, is that often the radial coordinate in these ingoing coordinates is the same as the radius of a transverse sphere. There's something similar happening here. So the radial coordinate in these ingoing coordinates happens to be the same as the dilaton for these on-shell solutions. And also it tells you about the dynamics of this RH. It tells you that the RH by dV is 0. So you've got this. This is a constraint. So it means that the only classical solutions are static. And that's because this theory doesn't really have any local degrees of freedom. There's no gravitons, for example. So if you don't have any matter, there's nothing to carry the energy away. So the horizon radius is static. And we can work out the Hawking temperature, and we can work out the first law. The only thing I'll emphasize here is that this entropy, in this case, is proportional you can check to the value of the dilaton at the event horizon. Oh, sorry, at this at the event horizon. I've allowed the possibility here of a constant term when you integrate up the first law. At the moment, that's just an arbitrary constant term. Okay, so I've got, I'm wondering whether I should probably wrap up in the next couple of minutes, so maybe I won't.
Yeah, let's say like in 3 to 5 minutes.
Okay, well, in 3 to 5 minutes, that means I think I can finish my discussion of JT. That's be a nice place to wrap up and talk about the Schwarzian theory. Okay, so there's another way to think about these configurations apart from these ingoing coordinates. And that's the fact that we've got this constant curvature condition, but the scalar curvature in 2 dimensions completely determines the geometry located. So it means that if you have any metric that satisfies this, it's got to be the same as pure ADS. So you've got to be able to write it in some coordinates, capital U, capital V, and this is the sort of Poincare ADS in like-cone coordinates. But the boundary here is at U equals V, where this factor blows up, but it's not, but the sort of time here, which is U equals V at the boundary, doesn't necessarily line up with the physical time that we defined by the proper time along constant dilaton. It could be related by some diffeomorphism, diffeomorphism F, or a reparameterization of time, if you like. So you can, if you change your coordinates capital U to F of little u and capital V to F of little v, you can write the metric like this. And now, again, it's a simple exercise to check that if you want to recover the ingoing coordinates that we had before, there's that this is the coordinate you need. And so this fixes the metric at, so it fixes the sort of 2 dr dv part of the metric. But then once you plug that solution back into the metric, then you need to read off this, the sort of horizon radius as a function of time. And it's given by this Schwarzian derivative. So if you're not familiar with this, this is a particular, you can write it like this, f double dash of t over f dash of t minus a half f dash of t squared. So this is a sort of this curious third derivative combination of our diffeomorphism. So because this horizon radius squared was giving us our action, in terms of this diffeomorphism variable, we can again plug this back into our JT action on shell, and we find this. This is the famous Schwarzian action, which crops up in other places. In particular, this gamma has, let me get this right, has dimensions of time or length. So it's a dimensionful coupling constant, and because it sort of appears, gamma appears where 1 over h bar would sit. Coupling becomes strong. So in particular, this theory becomes very strongly coupled. Quantum fluctuations become very important at some low temperature, and that temperature is of order gamma. So we'll think of, we'll have energies of order 1. So we're going to take solutions with RH of order 1 in ADS units, and we're going to take gamma to be much bigger than 1 for most of what we're saying, so that it's classical, or it's a classical limit. And the last thing to say about this is that not every diffeomorphism gives you a different spacetime. There's a redundancy if we take F to AF plus B over CF plus D for constants, say real constants A, B, C, and D, then we get back the same solution. It's, in particular, the Shortian derivative is invariant. This combination, you just have to plug it in, and somewhat magically, it turns out to be unchanged when you do this fractional linear transformation. Fine, and I guess next time I'll explain why this crops up in other places. It seems like a rather sort of special thing that just happened to come out from this special theory, but there's a way to understand this from a symmetry reason, which we'll start with next time. So with that, I'll invite any questions.
Okay, so let's first thank Henry again. Sorry, not again, but let's first thank Henry. And questions?
Yeah, perhaps. I would like to ask about the boundary conditions between the reservoir and the gravitational reason again. So in particular, you said we're going to pick just transparent boundary conditions. And I know you didn't want to talk about holography, but if I can ask a question about holography,
yep.
What happens if I try to integrate out the bulk or describe it holographically as just the reservoir with the boundary? I know from the literature people normally pick some conformal boundary conditions for this case, but this doesn't seem to play well with the transparent boundary conditions for which there should be energy flux. So I would like to ask if that's okay, or yeah.
Let's see. Yeah, so if you I mean, yeah, so whether you think about it as holography or not, you can always think about integrating out the bulk. And the bulk, actually, this is exactly how we're going to think about gravitational theories in general later. It's something that you take some boundary condition, and then you sort of do the integral over metrics, and it gives you a number amplitude. And so that is just the effect of integrating out the bulk. So let's find a square page later. So there's an alternative way of thinking about this, where you integrate out the bulk, where you have this flat space, and then here you have a sort of a defect. So this is yeah. So there's some boundary degree of freedom. In fact, it's going to have many degrees of freedom. So you can think of this as a yeah, a boundary condition, a particular sort of boundary with dynamics for our quantum field theory. I'm trying to think whether this is naturally a conformal boundary. I think the answer is not, because you have the well, let's see. It doesn't satisfy.
Right, because my question precisely at this point would be that the conformal boundary condition is fixed by exactly the absence of flux through the boundary, right? Because that's what gives Carnot conditions. And but in some sense it might be okay since you integrated out everything else, so maybe it's somehow encoded in the new boundary condition. But it's just that I don't know if there is some explicit integrated out version of this that you can compute and see what boundary condition comes out.
Yeah. So you could imagine. You could certainly imagine something like, say, SYK model. There's some quantum mechanics here with many, many degrees of freedom that lives here. And then there's some relatively simple coupling between the bulk and the boundary. But yeah, I think it's not going to be conformally invariant, because any conformal boundary condition, energy that goes in immediately comes back out. Whereas in this case, there's another way to conserve energy, which is the energy gets held in the defect. So energy can come in, say, forming a black hole. It then sits around for an extremely long time, and then it leaks out slowly later. That's what we're going to be getting. So yeah, I think it's not going to be a conformal boundary. It's going to be some more generic sort of boundary. Yeah.
Okay, thanks.
I'm not sure there's a terribly useful explicit way to describe that. But yeah, I think you could think of this as something with some quantum dot, some system with many degrees of freedom, and then you have a CFT living on a half space, and then there's say some simple coupling between the two. So maybe you couple to some simple local operator to determine the boundary condition for the CFT. But I guess yeah, there's
Is there any other question?
Yeah, can I ask a very maybe basic question? So in the beginning of of your lecture, you emphasized that you don't want to assume holography or string theory or anything. So do you expect that is it? But I guess you will be talking about non-perturbative effects, right? So at some point. So do you think about it as no matter what the UV completion is, it will not affect this discussion? And if it does not, why? And if it affects the discussion, then how do you think it might affect it?
So I think it shouldn't affect you shouldn't need to know all of the details. So I'm going to make a particular, what I think is a reasonable definition of what the low energy theory should do, or which is you, whatever quantity you want to compute determines a set of boundary conditions. So you know, if you were doing computing S matrix elements in quantum field theory, you would have some boundary conditions that define an in state in the Fock space at scri minus, an out state in the Fock space at scri plus. So that determines the state of quantum fields at scri plus. Then you integrate over quantum fields everywhere else. And I'm going to just take that sort of standard philosophy and say, that's fine, I'm just going to integrate over the metric as well. So that means that in particular, these asymptotic boundary conditions are going to fix the asymptotic metric. But other than that, I'm going to allow for any metric in a particular class. Now, precisely what sort of class of metrics you include could depend on the UV completion. So in particular, we're going to end up making use out of these replicable wormholes that have some particular interesting topology, and it might be that some UV theory just doesn't, for some reason, allow for those topologies. I can't rule that out, but it's a reasonable definition that seems more or less independent of what's going on in the UV. So it's not, we don't have to know about exactly what the higher dimension operators are and these sorts of things, but it's just in this, the question of whether my definition of gravity is, my reasonable definition of gravity actually pertains to a particular sort of UV completion, is where the UV comes in, but that's sort of some generic thing rather than details.
But I guess I just naively, it might be that none of the UV completions satisfy these games, like just for the, so.
Yep.
Okay.
Yes. Yeah, but I think before we talk about speculative UV theories, then I think we should make sure we understand the space of possibilities of what the IR, what the long distance physics is telling us. There's been a particular story for many years about what long distance physics tells us about black hole evaporation, and that is famously in conflict with ADS-CFT and so forth. I'm going to tell a story that is saying, again, we're going to take this low energy starting point and come to a different conclusion about black hole evaporation. And actually, it's still not going to agree with ADS-CFT in the end. But it's a different point of view that lends a different perspective on what the low energy is telling us. And we have some confidence because it's giving us answers that are some answers that are extremely sensible and things we expect from quantum mechanics generically. So, but I can't, it doesn't come with guarantees.
So if there are no other questions, then okay, so let's thank Henry again. And see you everyone tomorrow, hopefully. And can you, well, if you don't mind, can you put the links to those those notes in the Slack, Henry?
Yes. Yeah.
And people can also ask questions, more questions in discussion.